Okay, I guess we can start first, and more people will join later. Hello everyone, welcome, and thanks for joining today's sessions. And we are excited to have Taro here with us today. Taro is a co-founder and CTO of remyx.ai. Taro has over 10 years of experience applying machine learning exercise across healthcare, robotics, and content systems with a math background from UC Berkeley and UNC Chaminghai and Remyx. He's focused on building the infrastructures that makes AI experimentations more systematic and production ready. And today he will introduce GitRank. Terry will share how Remyx is using GitRank to help automate the process of building a pipeline from research paper discovery to testable code integrations using multi-agent systems. And he will walk us through the practical techniques from automatic validation workflows, scalable testings, and bridging the gap between the research and practice. Yeah, thank you, and Tara, yeah, you can get started. The floor is yours.
Thank you. Thanks for everyone who's come to check it out, and appreciate the opportunity to speak about what we've been working on. So as introduced, we're talking about GitRank, and the idea with this pipeline is to identify relevant new methods that are being published on the arXiv and match those to practical engineering challenges that teams are facing so that they can implement those core methods from the papers as testable PRs for their system and replicate the work, validate the work, and find ways to improve their systems faster. And so on this top slide here, I'm kind of showing an example of one of the draft PRs that we were able to open. And this is almost done in a completely automatic way because of the pipeline I'm about to go into describing. We were able to implement draft PRs to test some new code that was referenced in an arXiv paper to try to get inference optimizations for a VLM that we work on. And so I use some of the projects that we've put out in open source as a seed for some of the work for us to sort of dog food our own product and understand like you know what the failure modes look like and improve upon it. So let me get started. To start, I want to talk about what's broken in the discovery process around finding new ideas. You know, we all are probably following some of the same influencers on X and LinkedIn and elsewhere. And what you find in these platforms is every day there's some new paper that everyone's hyped about, and it sort of dominates the feed for discovering new methods. But the reality is there's hundreds of papers being published in AI and in machine learning every day. And so many of those papers are maybe overlooked. Sometimes it's because the domain specialization of the paper is making it more of a niche interest to people working in that area. But a lot of times those same methods will crossover transfer to problems that you're working on. In the course of making GitRank, I've been surprised at how many times I find a paper that is not being discussed. It's a repo with 0 stars. It's applied in some domain specialty that I would have probably ignored the paper. But because LLMs are so good at ingesting all the context of the paper, and because we're introducing the context of the code, it's does a pretty good job of matching some of those techniques and methods to a sub problem that I'm facing as I'm trying to improve my own code. And so, you know, when we see these papers that are dominating the feed, you know, some tweet that's going viral, it's important to ask ourselves, as excited as everyone is about this new breakthrough, this groundbreaking new research, how practical is it for us to actually use the work to replicate it to solve our own problems? And I would say that when you start to think about it that way, you realize lots of the stuff that people are excited about maybe is of interest for being read in on where technology is going, or of some theoretical interest, but maybe practically speaking is not that usable for your own problems. And so I wanted to start thinking about how to improve discovery. And as I mentioned, I was mostly seeing the same papers on social media. You could go to a place like Papers with Code, which has now been retired. You could go to a place like Hugging Face Papers, which has a team working over like the exciting new results and curating them, and it has people upvoting them, people who are generally more read in on the state of the art. And so it's a bit of an improvement over just scrolling through your feed and hoping to find something useful out of everything in there. But what we wanted to do is really personalize the papers that are recommended to users based on the context of what real world engineering challenges you're facing in your use case, in your application. And so on top of that, we wanted to be able to filter for how usable would it be? Like, does it include links to runnable code? And beyond that, we would like to be able to test the code, test the quick start in a environment so that we could replicate even the most minimal version of that quick start to understand if it was worth digging into deeper. And going beyond that still, ultimately, it would be ideal if when we've found a paper that's relevant and it does include code, and the code's in good enough shape that you can practically automate the construction of a Docker image, or you can verify that the quick start runs smoothly, then it would be ideal to be able to take that code and identify the core methods, the most important part of that code, and actually implement that in your own repo. So could we turn these brand new methods that were published maybe yesterday into a draft PR without even having to do a bunch of vibe coding, chat back and forth, copy pasting context around, or things like that kind of make it difficult to implement in new methods using like the existing tools. And so, to frame this around, the existing tools, AI-assisted coding, AI-assisted engineering, vibe coding is currently great at implementing a demo, a V0 version of something. But once you start introducing enough complexity for a real-world application, it struggles. And a lot of people have found this to be a limitation. People are still trying to figure out how they can use these technologies to speed up their coding and their implementation without removing a bunch of important code, or being stuck in back and forth conversations, feeling more frustrated and feeling like maybe they could have implemented it faster manually. And so, we want to think about ways to remove that synchronous back and forth interaction in the coding, and do as much as we can sort of offline before that context is introduced to a developer, so that they have workable examples that have been vetted more, and they don't have to basically reintroduce all the context of what they're building every single time they bring up one of these tools. It sometimes feels like Groundhog's Day, where you're teaching that junior developer all the context of what you've been building at the beginning of each of these like coding sessions. And so we want to be able to externalize that context and use the agent to work over that asynchronously, so that when a developer is notified about some changes, it's been pushed much further along in the development process. Another shortcoming of LLMs that we want to think about here is that they're great at generating code or tokens from the mode of the training data, but they do struggle with creativity and originality. And so asking an LLM just to try to produce like some new idea is usually not very fruitful. We should expect the underlying technologies to continue to improve, and yet this is sort of inherent to machine learning and AI and ML systems, that they're good at predicting average, but they're not so good at like I guess predicting like very original things outside of the training data distribution. And so this is a picture I have in mind that I had found from a LinkedIn circulating around. And I think it says a lot about what I was just speaking to about an LLM's capability. And our idea was, as I said, to source some of these creative ideas from the research that's being published on the arXiv. So how can we use the strengths of humans who are surveying the results and thinking hard as teams over long research cycles, really trying to push the state of the art and find something worth publishing to the arXiv? How can we use those insights alongside the strengths of LLMs, like fast implementation and a breadth of knowledge about coding best practices, about different libraries, etc. So this is where we came up with the idea of sourcing the core methods from brand new papers that are published to the arXiv every day, and using that to speed up implementation and testing with LLMs. And so as we're thinking about why we think fair new code is go to zero. There's many vendors who provide some kind of automated testing tool. There's automated PR reviews. So the ecosystem is getting full of people who are attacking different parts of this problem. And LLMs have especially found fitness in the coding problems, because that's a large chunk of the training data that they work over. It's an important and valuable problem. The people who are closest to pushing the state of the art with AI and LLMs are often coders, and so they're trying to speed up their own productivity. So we say that the implementation cost is going down really fast, but ideation and even robust validation are the bottlenecks that are at the frontier still for this kind of technology. And so we're trying to help teams find fitness by staging draft PRs. And we think that this ultimately will allow them to concentrate more on deeply understanding the methods that are working, where there is testable code, spend less time trying to set up environments, less time reaching dead ends with code or ideas that aren't quite there. So if we could make this like an asynchronous process, then instead of doing a bunch of back and forth and vibe coding, engineers who are basically research adjacent, when you're thinking about like AI and ML engineering problems, they can go dive into the paper and get a deeper understanding, maybe figure out a way to push that draft PR further, or even push the idea of the papers further if they're inclined to. So our plan for building a system like this is to scan the metadata from new arXiv papers, and that's just using the arXiv's APIs. So we can query, several hundred new papers from the arXiv daily. You can poll for new publications if you want to get them like hot off the presses. But after that, we want to match and rank for relevance the papers, the core methods to the users and the applications they're building, the specific engineering challenges they're facing. So you could imagine somebody has an LLM, a VLM, some other AI, ML application, and eventually the code around the model might begin to stabilize as they're running and deploying these applications. And the model artifact itself ends up being one of the parts of the pipeline with the highest capacity for optimization. And so, if it was worth building and it's worth maintaining and optimizing, if it's an application that users enjoy and it's making money, you're going to want to spend more time really chasing the nines to improve performance for that application. And our idea is that, at the model layer, at the foundation model layer, this is a really high leverage place to be focusing on experimenting and continuously improving to make the application better for your users, for your business. And so we can start by simply matching relevant methods to the developers based on the context of their application and use case. We can do simple things to skip code that just has placeholders or links that dead end to a 404. And going beyond that, as we want to scale to not just ourselves, but maybe many users, we would like to pass from bringing all of the context of hundreds of papers along with the context of what you're building into an LLM to ask for that ranking, and instead use document embeddings. And we want to think of this more as like Google Alerts than Google Search. And so we use Elasticsearch's Percolate API to make the best matches for our users. And one way to think about that is the context of the problem that you're working on from day to day is not changing that fast. And that's part of the problem with vibe coding too, is you do have to keep reintroducing a lot of context between sessions to get good output from the models, from the LLMs. But if the context isn't changing that fast, then we can think of this like alerts model using the Percolate API. And if you're not familiar with Google Alerts, the idea is this. When you're doing search over an inverted index, you will index the content so that at a query time, a person can input some ad hoc query and then get hits that are most relevant to that query. But if you invert that relationship, then you can actually index the context that a developer is working on over the weeks and months and so on. And then as a new paper is published, index that to find hits on which users would find this relevant. And that allows us to make this kind of a pipeline that's more of a push model than a pull model. So it feels like the agent is doing something proactively for you and not waiting for your query to return relevant results. So I call that the easy part because, everything I've described about the Google arXiv APIs and feeding that context to an LLM for ranked results, all of that could be done in a Colab notebook. And that's actually how I started prototyping this idea, I guess in May or June. But what we really would like to do is test the code further. And often you can look at the code and verify that there's actually code there, but you do need to run it to know if it's going to work. It may look like it'll work, and for one reason or another, there's parts about it that are broken or misconfigured. Often researchers are doing little things that you wouldn't accept in a production coding environment, like hard coding paths to where they were storing the data and things like that. So these are like little things that we should be able to catch and fix to make the code more usable for people who want to test those core methods. And the first thing that we decided that we needed to do is to try to create Docker images around the repos. Most research code does not include a Docker file, so it's not trivial to find a repo related to an arXiv paper and just build a Docker image and find a runnable quick start. So that's the first problem that we need to overcome to try to test or vet the code, make sure it's usable for people. So here's a diagram to have in mind that kind of walks through the parts of the process that we've talked about already, mostly in the blue section, and the parts that we're about to get into. Probably the more complex parts of the whole pipeline are really in setting up the environment and doing testing and repair loops to fix little aspects of the code. So at the top, you see over here app history and interests. That could be information about your repo. It could be information from a blog about like a engineering blog about what you're building. It can be pretty high level context. A lot of times I've used the context of a model card README for a Hugging Face model artifact that I published related to this work with VLMs. And so the description about what problems you're solving, what the limitations of that tech are, the different ways you've been evaluating those models, all of that stuff can be relevant for helping you figure out new ways to speed up your model if inference optimization is important, or to find new benchmarks so that you can validate the models in a similar way. So all of that context comes in along with the archive metadata, like I said, which is available through the APIs. We would get like several hundred new papers along with the context of the application and use case, and prompt an LLM to just rank the papers for relevance to solving like practical engineering challenges for your use case. In the green section, it's about taking the ranked results and finding links to the GitHub, and using tools like Git ingest is a repo you could check out that's designed to help you ingest all the context of your GitHub repo so that you can put that into like a format that makes it easy for LLMs to analyze that context. Also find different model artifacts from the hub, and use the model and code artifacts to then create these Docker files that we would use as the environments so that we can start testing the code and modifying it. And so this green section in the middle is really where a lot of the work happens on generating a Docker file, testing that it builds, and ultimately in the red section, deploying an agent inside that Docker container so that we can test the quick start methods in an environment that has all the dependencies sorted out and has the right hardware interfaces available so that we can provision GPUs or do things with security so that we lock down the network and are limiting the attack surface, because we have to remember testing code in the wild that hasn't been inspected by a person is a risky business, and you want to make sure that you have access to the right tools to test the code in terms of having an API key that you might need for running those models, while also not finding that you're getting you're running into a prompt injection attack that could be used to exfiltrate those API keys. So to build the environments reliably, I mentioned Git ingest. It's a tool that will allow you to point to a repo and gather all of the code and structure of the repo so that you can bring that context into your LLM with tools agent, and use that to try to make decisions about, what the Docker environment dependencies need, what the Docker image dependencies need to be, or what code actually points to like the quick start or minimum demo that you want to test with first. And we're using we're prompting an LLM to first generate a Docker file. And with AG2's reliable tool, we can wrap a function that's designed to eat that Docker file and test build it. So think of a function that takes the Docker file as input and basically uses subprocess to build a Docker image. And if it can return a build success in the output, then Reliable Tool will be able to parse that and identify the task success. And so Reliable Tool is essentially allowing us to use like a React loop to have LLMs run these tests in a sequence until it either determines it can't build it or it determines it's completed the task. And when we've done that, when we see build success on our attempts to build a Docker image, we can push the images to the hub, which we've done for nearly 1,000 arXiv papers over the last 2 months. So we find, you know, that the number of papers might be hundreds a day, and the number of papers that have runnable code drops off considerably. And out of all of the papers with repos linked to it, the ones that we can automate the building of Docker images drops off again. And it's something like, you know, 3, 4, 5% or something like this for being able to like build and test all the images through. And as we improve our system, we expect we can bring that success rate up too. But there are some repos that you're going to run into that for one reason or another are just not well set up to automate the testing all the way through. And so in this slide, I'm pointing out that of all of the prompts that are used in this system, the most complex one is the one that's involved in making the Docker files. And so I include this little image I sampled from a paper, and I'll try to share these slides around. I do in the comments or the notes section of these slides link to references so that you can read more about these papers that I'm citing here, or also the blogs. We've been kind of building in public through Substack, blogging about these components as we were releasing them through the summer. But this slide is pointing to just how good modern LLMs are at successfully completing many tasks. Like maybe you can give an LLM 100 different I guess instructions in a prompt and expect it to complete those at a high rate pretty consistently. So our most complex prompt doesn't go near 100 different instructions, but it is pretty involved. It involves prompting the model to use buildkit here docs so that the Docker file is entirely self-contained. So that means like you might want to run a shell script or a Python script that doesn't already exist in the repo. And so just building the Docker file alone might not bring you to a place where you can run the minimal demo. And so this allows us to fix things in the repo itself and then extract like simple demos that might even simplify over like the main quick start result that's presented in the GitHub. And so we can make a single self-contained Docker file and test that and run it through. And some of the biggest challenges in making it build and having the dependencies handled involve just matching Docker images that have the right PyTorch version, CUDA compatibility. A lot of the code that we're running is going to use GPUs. So when we're doing these tests, we're doing it on instances that have GPUs that we can run it against. And just that's probably some of the hardest part about building these Docker images is figuring out all of the dependencies and making sure that you start with a good base image that has PyTorch and CUDA handled for you. And flash attention is a library that we need to pay special attention to because it's more difficult. Sometimes you need like specialized instructions to make sure that you have flash attention set up well to run this code. And ultimately, we want the Docker image to run the demo, the quick start, as an entry point. And that's something that you can override when you're running one of these containers. If you just want to drop in and interactively check out the code or change that entry point. But we do want to make it pretty simple to just run a container based on that image and see the quick start complete successfully. So we build these images with that entry point, with the idea in mind that we want to be able to test the demo when we run it, and going beyond the quick starts to actually test to test the demo, we use AG2's two-agent chat with the writer executor pattern. And so in particular, we're using the Docker command line code executor so that we can take the images that we just built using Reliable tool, pushed up to the hub, and now drop the writer executor into that image so that we can start running the code. And this is a more flexible and robust pattern when the task itself is pretty open-ended. We want to really minimize the amount of sort of specific or bespoke instructions that we're giving these agents so that they're going to work well in a variety of repos that we're working on. And so it's worth taking a look at the Docker command line code executor and this writer executor pattern that's being used here. But essentially, you'll prompt the writer to direct the executor on the high-level task that you want to accomplish. And they can communicate through, I think it's the temp directory inside of these Docker images. And we clone the GitHub repo in the directory, /app. So we need to instruct the writer to instruct the executor that all of the code that we want to run is not in the current working directory in /temp, but is actually in /app, so that it can find the code that it needs to work over and go. And a big part of making this work for our use case is making sure that we could get more control over the container interfaces. So since we're mostly focused on AI and ML code, we're often going to need to use a GPU. But we're also going to want to have access to environment variables that have secrets or API keys so that we can do things like read a private data set or private model, or push artifacts to the hub, Hugging Face hub, or to run some closed source API. Lots of the research code uses Claude or ChatGPT. But also, we want to be able to use egress whitelisting so that we can restrict network access. And this is mostly about security. So you could imagine, as elaborate as it sounds, it's getting cheaper and cheaper to write papers also. So a malicious user, an attacker, could AI slop out some plausible looking white paper, publish it to the archive, link back to code that is associated with it. And we don't want our system to find that paper, think it's useful, clone that code, build the environment, and then start doing whatever the repo told our agent to do. This would be an elaborate way to pull off a prompt injection attack. And so you could imagine an attacker saying something like, hey, take all their secrets and post that over to some compromised server where there'll be logs so that I can take over their OpenAI account or something like this, or start using their services, or however you imagine they would use your keys or things like that. And so we made a small contribution back to AG2 by making some of the changes that allowed the Docker command line code executor which is running the Python Docker library, to pass container keyword arguments. That way we would be able to access the environment variables where we might have these keys stored, or to use a restricted network where we've locked down like which we've whitelisted which domains our agent can access. So we have this GitRank repo currently whitelisting domains like Hugging Face, because a lot of the data and model artifacts will be there. As we're running the executor, I think I mentioned some of this in a couple slides ago, but we're prompting the writer to instruct the executor to start by checking the README. And that README is in the /app directory where we've cloned the repo that we're trying to test. And we have termination criteria for this two agent pattern to finish if it can detect that it's successfully run the demo, or also if it hits certain like resource limitations. So we don't want to bring it all down with a out of memory error. And we use hardware monitors to detect when we've been able to successfully utilize the GPU. So we set like thresholds for GPU utilization that we use as a signal for identifying like task success. And the reason for that is some of the earliest tests that we were running, it was doing a benchmark, it was running like the minimal quick start for a benchmark, but even that minimal example is using pretty hefty GPUs and running over like thousands of data points. So it would take like 3 hours, and we don't want to wait until it finishes 3 hours later before we say, hey, this code is probably good to go. So we can threshold on certain GPU utilization and identify that as termination criteria to end the conversation. And some other tricks and tips are to prompt the writer to prompt the executor to use like command line tools like tail instead of cat. So the difference being the amount of output that's going to be. We were gravitating mostly towards Gemini because it does work over a very long context, but it's possible when you're using cat on some of the files that are generated to overflow that context. And so we also use the message token limiter to kind of limit the context that these LLMs are considering when they're deciding on the next step or if they've completed the task. And we've also made use of AG2's max consecutive auto reply to just limit the number of conversation turns that we'll let these two agents go back and forth in before we say it's not working and we need to just call it a failed task. So practically, maybe 30 or 50 turns is good. You don't need to let it do anything that's unlimited, or even maybe anything close to like hundreds of turns. If it doesn't succeed pretty quick, then you're basically determining that the repo itself is not packaged well enough to make a quick start. And that's not to say that it won't be of interest to engineers and researchers trying to replicate the results, but there is a signal in knowing how much work it's going to take to try to bring that environment up and to run that demo. And so we want to especially make the low-hanging fruit even lower, even easier for people, so that they can quickly decide like how they're going to triage these options and work on things that are going to be like fast to test. So checking the executor success, we use AG2's hooks to log conversation traces. And we also use threading so that we can monitor GPU utilization, CPU, memory. All of that is being monitored and using thresholds so that we can pass a signal to the agents so that they have the context to terminate the conversation. And so this is hooks on the logs and hooks on the hardware monitors with threading so that we can run this in the background. And ultimately, after the conversation terminates, we're prompting an LLM to judge the task completion based on the output of those logs. So the reason why we want to log these conversation traces is it is possible for an agent to do something, even something that is using the GPUs, but that something is not actually completing the task. So they need a lot of verification to make sure that it's not kind of stumbling into a path that at surface level might look like a task success when in fact it's not. And we found LLM Edge Judge does help us to analyze the logs and make sure we don't have too many false positives in this. Another thing we've used from AG2's framework is teachability. So we aren't expecting to necessarily complete the task in the first go. If we can bring the success rate of task completion up enough, then we should expect it's very hard to fail multiple times in a row. And if we're using teachability, that's worth looking at in the API docs. It's going to allow you to cache more of the information about the previous runs and actually tie into that context directly with the writer and executor, so that you can hope to avoid repeating a mistake that led your conversation astray in the previous run. So I'll just say that building these images, of course, is time consuming, testing them even more so. But we have hundreds to work over, and it wouldn't be possible to scale this up without distributing the work. And so what we did end up doing is implementing this test loop using Ray actors. So that allows us to run multiple tests at the same time. And so we can scale up to machines that have multiple GPUs. We can scale to multiple machines. So partitioning that work and distributing it across more machines with access to more GPUs allows us to move through this a lot faster. And this image is sampled from, I would say, a related work. ByteDance, around the time that we were doing a lot of this stuff, ByteDance had made a publication of a work called Repo to Run, and they were interested in automating the creation of Docker images. I think also from arXiv papers, or maybe they weren't, doing this for like general arXiv papers in this pipeline we described, but they were interested in automating the creation of Docker images from repos. And so they had an interesting diagram here that says like that for humans, the average time to building these images might be around 30 minutes. And they were able to build these images in 20 minutes using their automated pipeline. So it's worth taking a look at that paper and learning from what they did. And as I said, we were trying to scale this up to many more repos, and so we wanted to be able to distribute it and see if we can bring the time to creating these images down even further. So now that we're finally at a place where we've gotten past the top of the diagram I had mentioned earlier and past the green section where we were building Docker images and testing that, or building Docker files, testing that we could build them successfully. And even in the bottom of the diagram where we were using this agentic loop to test the quick start inside the Docker image that we built. we ask ourselves, how can we take this even further? Because it's great to find relevant papers. It's great to get a Docker file for these research repos and even fix them or verify that the quick starts run. But ultimately, knowing that the quick start run will run is a signal, but it's not really what you're trying to do if you're trying to replicate the result or use the same core methods in your own repo. And so that's the next question we started to ask ourselves as we were building out this GitRank pipeline, is if we could take our repo and paper recommender past testing it out and actually use it to implement the core methods in your repo. And, you know, it kind of begins with asking, like, what's a practical test so that you could improve your application, because the goals of the researchers are not often perfectly aligned with your goals, trying to build an application that uses AI and ML artifacts or wants to adapt a method from one domain to your own. And in this, we mentioned at the top of this that we don't want to slip into a workflow that is synchronous, where you're copy pasting a bunch of context back and forth. We want to see how far we can go automating this as far as we can. And so instead of the prompts that you have to use for vibe coding, we're thinking of the code as this paper, how this code could be relevant to your own target repo. And so we're focused on practical applications of those core methods, trying to do a minimal test on the claims of the research paper and adapting it to your use case. And again, we use git ingest for now your target repo. So we have, in the context of an LLM, information about your target repo, information about the source repo that's related to the research paper, and information about the environment, the Docker image that we were able to build, so that we could take these pre-built environments, which are a step further than the repo is towards like making it runnable and easy to replicate, and a step closer in like vetting that the quick starts work, and take all of that context to try to implement a draft PR for your target repo. And so that's the idea I'm describing here, is to bring the context of both of these repos together, along with whatever we've been able to learn by building the environments and testing the quick starts, so that we can create a minimal, practical experiment that introduces the core methods of that paper into your repo to solve a practical engineering challenge. And once we have that test PR, we can do the same thing as we described when we were testing the Docker images, by dropping this two-agent writer-executor, dropping these two agents, the writer-executor, into a Docker image. This time, a Docker image built for your target repo, but including information we learned about the source repo, its dependencies, and using the same techniques to test through the minimal way of verifying that this draft PR can work. So using the monitors and LLM image judge to evaluate the successful completion of a test of this minimal PR. So I want to talk about the limitations of a system like this. It's been something that we've been able to find success with when we're talking about implementing the PRs, the draft PRs, on a mono repo. But some code spans multiple repos, and so you're going to run into challenges trying to bring all of that context in, and that's at the frontier of like what we think is necessary to make this even more useful for teams that are trying to improve their AI and ML pipelines. It's primarily targeting AI ML code and methods, and that's not something that we're so interested in moving away from for the time being. And that speaks to the point I made at the top about where's the leverage in working with these pipelines, and we think it's around like focusing on the model layer and ways to improve that through inference optimizations, through new fine-tuning regiments, and that can include code around your data curation, data synthesis strategies too, that feed into like fine-tuning and these other kind of AI engineering workflows. But we also want to think more about security layers to limit the risk to prompt injection. What I described is that we've been able to take in the context of the repo, and we've been able to build Docker environments. So we are protecting the machines from being, I guess, bricked or something like this because of a prompt injection attack that got into a repo, that got into an arXiv paper. But we also talked about how we can restrict the container interfaces, especially like the network, so that it makes it impossible for the agent to phone home on some malicious server. And I can still imagine an attack where somebody has created a repo and a paper and gotten indexed, and the agent was instructed to grab all the secrets and create a Hugging Face data set, and then publish the secrets to a Hugging Face data set that's publicly available, perhaps tagged, so that a researcher could easily just look for data sets tagged with, their special word, and start exfiltrating credentials that you use to run this stuff. And so there's more layers. There's ways that we can use ephemeral tokens. We're doing this as an offline process, building these images with our credentials. So, doing this and doing it in the cloud and doing it with these restrictions has made that a difficult attack to pull off, but we need to make sure it's impossible. We need to do more to verify, like the repos, scanning the repos, ensuring that there's no instructions like that can leave it vulnerable to exfiltrating our credentials while we're building these images that we share. And just generally, we need to think about ways to improve the overall success rate so that we can get more of the buildable images built, and not lose like valuable ideas because it was difficult for our agent to build the images. I guess this leads me to the services that we have available. Explore is one that focuses on finding and matching relevant arXiv papers to your interests, the engineering challenges that you're working on. And when you find a matching paper, if we were able to successfully build the environment, we have this ideate service for implementing the core methods from that research as a testable draft PR for your target repo. So to wrap up, the AG2 documentation and tools have made it easy for us to solve a lot of the problems that arise from having a sandboxed environment to build and test the code in, to dealing with the huge context that some repos have, scoping that down and making it easy to use LLMs to work through the different challenges that arise as we're trying to test these quick starts. And in the end, we have a agentic system that's able to help people find new methods faster than they would have from scrolling social media and hoping to find papers or methods relevant to their work. So instead of finding that paper weeks, months, sometimes years after it was published, we can really accelerate teams like discovery and implementation of those to try to help them lead in how they're using this technology in their AI stack. So with that, I have reached the end, and I thank you all.
Thanks, Terry. That was awesome.
Thank you. I guess I didn't realize it would take the full time. It's
all right. But actually, I did have a few questions myself, because I actually, other than being a maintainer with AG2, I have my own product, and it's related to code. It's but let's just call it a lovable clone, you know? And the one thing that I had always dreamed of my vision was a value engine, a value creator. And that was my dream of the first part of it was being the arXiv search to find those true innovative products or innovative things that are coming out, so that the platform could have the innovative integrations. And this is like the perfect integration of that. You know what I mean? So I find that very interesting, and I'm going to look at it myself.
I think it is the problem, and I didn't get to speak to it in this because the pipeline I'm describing is really focused on more of that top of funnel, like discovery and ideation. But what we're really trying to do is get to a place where we can help people ramp up the testing all the way to production, even doing things like A/B testing, because in the end, it's not just testing ideas or even optimizing a pipeline, but it's like learning what matters for your users, because the space of possibilities is so big. You can't possibly just try everything. It's like you really need knowledge to guide you through that space, so that you can double down on the things that work and have a deeper understanding for like which candidate PRs are worth pushing on further. So we think about this feeding into like a full cycle around AI experimentation, where we're helping to surface new ideas, we're helping to implement them, but ultimately we're trying to test them into production deployments and use like controlled experiments, like really methods with a lot of sensitivity and the scientific method for verifying those ideas. We want it to build into a knowledge base, because each of these PRs could be like tagged or mapped to like, this is an inference optimization, this is a data curation strategy, and we could learn empirically like data curation strategies are really working for this pipeline. Let's source more methods like that. So this can feed into the recommendation system too, to really build like an AI co-pilot for your whole experimentation process. And there'll be parts where an agent is better, more helpful. There'll be parts where a human really needs to get in the loop and validate things, to do like more data science to make sure like the changes you are deploying are going to like work well for your users. But I do think that there's a chance to use AI through the parts of the workflow that are kind of traditionally ignored by like DevOps and MLOps tooling.
Yeah, and like the percolate query, that was like another thing that which is another tool that I've been thinking it's actually a really good tool, and that actually helps a lot with that type of stuff. So
yeah, I love Elasticsearch, and we'll probably next time we talk, I might be using something else too, but I've been using Elasticsearch for so many projects over my whole career, and I'm a big fan of like the control you get over search and like relevance. So I'm pretty likely to like stick with that and use it more. We've been trying more recently to like support more of the search part. I mentioned like that this is about alerts and not search, but of course search is really important too. So we want to help people not just get notifications about a couple papers that could be relevant, but really help them like mine the archive for the times when they need to do that too.
Sure, you have anything you could add?
Yeah, this awesome. Thanks, Harry. Thank you so much. The product is super interesting, and it's actually a perfect example that I want to use for a tutorial I'm going to give tomorrow. The tutorial is at a conference called REXIV. It's for recommendation system. It's happening right now in Prague. I didn't go, but I will present online. And the topic I'm going to present is agentic recommendation system.
That's awesome.
Yeah, so I think it's a perfect example. So, so I really want to kind of introduce this project there. And it's very timely. So this talk is very timely, so that I learn about this project and can share with all the real audience.
Well, thank you. I appreciate the visibility, and I'm really interested in the recommender systems problem myself too. So I took a lot of inspiration from time I spent on a team that was doing like Rexis for video streaming, and it's like informed my understanding of this process of like the offline testing that's required, and you know the data science workflow that's involved before you can ramp up to like an A/B test, and you know the post experiment analysis that's involved. So I think a lot about this is like ways to address some of the shortcomings in AI engineering, which is like kind of leaned towards maybe skipping A/B tests and relying more on LLM as judge for evals, and you know sort of de-emphasizes even some of the like working at the level of data and weights. So I want to see AI engineers more empowered with those technologies too, to like really optimize their systems, because once we're past the demos, it's like I said, like going to be the most valuable part of your stack to really optimize. And in Rexis, like they devote whole teams with dozens of people just to improving the ranking algorithms, like with a new experiment launch every other week. So I think there's a lot of value to like looking to the Rexis problem, where you don't have like really clear cut metrics to say this is the best model, and like using what we learned from Rexis to these problems with AI engineering, where it's like very open ended.
Yeah, that's great. Yeah, so I guess the slides and the recording is shared. Can I use some of the slides you have today?
Absolutely. I can share you. I don't know if you might have a link that still gives you the most recent version, and I'd be happy to share it. And let me say too, for anyone who happens to be in the SF area on October 30th, that yeah, we're putting on an event, and so we're bringing people together from all kinds of industries that are thinking about how to experiment with and optimize AI. And so I'd love to chat with everyone here. Like more, it's kind of part science fair, part book fair, part Halloween costume party. So it should be fun, and there'll be lots of breakouts, and there'll be some pretty incredible experts in this domain of experimentation to chat with and learn from.
Yeah, I'll be there on that day.
Hey.
Yeah, share the event on Discord, please. Okay, thank you so much. I got to go.
Thank you.
Richie. Anybody else have any questions? I don't see any hands, but other than that, man, I like what you said. So maybe if you want to wrap it up there, that'd be great.
That works for me. And if anyone thinks of something later, I'm happy to respond by LinkedIn or Twitter or any of these places we're looking for new ideas.
Yeah,
so,
where I was about to ask, how could I find you?
Terry Rodriguez on LinkedIn, and on Twitter, we have a Twitter handle, smells like ML. We have a Discord that we maintain called the Build in Public Zoo. So we're around, posting on Reddit and stuff, and however we can connect, I'd be happy to chat further.
Okay. All right, great. All right, thanks, Terry.
Thank you.
Have a good one.
Take care.